Polar form. Last time we introduced complex numbers, but in this time we're getting to the real stuff in complex numbers. Writing things out with a new notation, and there's such a powerful tool for solving some really tricky problems we're going to tackle later on, and also roots of unity and DeMoivre's theorem are all going to be covered in this video. Okay, so starting off, the argument of a complex number. That's just the angle. So if we have a complex number a plus bi, this argument is just tangent of theta. You can think about it like, okay, that's B. So tangent theta is B over A. And then if you want to solve for theta, you just do tangent inverse both sides. Now, the magnitude of a complex number, or modulus is another name, we covered this last time, is this distance. And polar form is another way we can write complex numbers. And if you did I'm not sure which school course they covered this in, but maybe pre-calculus or something. But you probably are familiar with this, how you have a plus bi. Rather than writing as real part plus imaginary part, you write it as, okay, this is r, which is nothing but this. And then you write it as cosine theta plus I sine theta, or r cis theta. So it's like, okay, r is like the base value, it's like the magnitude. And then you're multiplying by the cis theta term. And this cis theta term is basically like how much we're rotating by it. So r cis 0 would be 1. R cis theta would just be like this point over here. And this is going to be equal to a plus bi. And cis, what is cis? This is short for cosine plus I sine. You can see here, CIS. Yeah, I mentioned that here. Yeah, and how do you actually get this polar form? Let's go through it. It might be, I think, a good exercise to go through how we actually get this. So let's say this is A and B. Cosine theta is just A over R. We get A over R. Sine theta is B over R. So if we expand this all out, we get this. That's kind of the neat proof for this. And this is super, super useful. It's a really good alternative form for writing complex numbers. And something else that we can probably add here is this cis theta term is also equal to e to the I theta. Okay, now that we've talked about, and I mentioned it here, never mind. And there's some cool identity of this, e to the I pi is -1. This is the most famous equation in math. One of the most famous. And it's kind of miraculous if you think about it, right? You got e, just like 1 over 0 factorial, plus 1 over 1 factorial, plus so on. You've got pi, which is 3.1415. It's this really random infinite number, which we don't even know exactly what it is. It's infinitely many digits. And then we've got the square root of -1 here in the power. You multiply that all gives -1. It's pretty cool if you ask me. You got 3 unrelated, the most random constants ever. You just give this. Pretty cool. Okay, now we're on to roots of unity. And rather than dealing with the generalized form, let's just take an example. Let's say we're trying to find out when is this true. Find all solutions to this. Now, if we were in the real numbers, if you were doing the AMC 10, it was just w equals 1. Or let's say you're doing the AMC 12. Now, that's not good enough. So here's kind of the idea behind solving these types of problems. And actually, just to make it a little bit more interesting, let's just have w cubed equals 8 to demonstrate roots of unity. So the first thing that we can do here is write w in polar form. So let's say r cis theta. Now we have r cubed cis theta cubed equals 8. So now here's the thing. This theta always has it does not change the magnitude of the complex number. R is an integer. This theta is kind of just rotating the complex number. It's not going to change how far away it is from the origin. So for this point to be 8 distance away from the origin, in order for w cubed to be 8, our point must be 2 away from the origin. Because then now we would have 8 cis theta cubed. If this was something else, let's say 3, then we would have 27 of this. And this would not work because this has a magnitude of 1. This point, w cubed, would be 27 away from the origin. Okay, so now we can just divide by 8 to both sides. We get cis theta cubed is 1. Okay, so now what are the possible values for theta? Clearly, theta can be 0, right? Theta equals 0, that would just give us the solution to cis of 0, which is just 2. Okay, but it turns out, in fact, that there's going to be 3 solutions, 3 complex solutions. Only one of them is real. And they're all going to occur at equally spaced intervals. Here's kind of the neat thing, and before we get into this, let's actually quickly go over DeMoivre's theorem really quickly. We'll come back to this slide later and cover it in more detail. But for now, the idea is that if we have cis theta, the idea is let's say we have a point in the complex plane, a plus bi. Now, let's say we multiply this point by cis of theta. What it's going to do is it's going to take the same point and if you want to multiply it by cis of theta, it's equivalent to rotating it about the origin theta degrees counterclockwise. So the idea that's kind of what we were thinking about earlier, right? Of how cis theta just rotates a point. It doesn't affect the magnitude. So now, what happens when you rotate it one time? Let's say you have a point. Let's say 1, 0. Let's say you have 1, 0. Let's say you rotate it by theta. You get here. You're at a point or let's just say not 1, 0. 1, because the complex number is 1. Now you're at 1 times cis of theta. Now let's say you rotate it again. Now you're at cis of theta squared. Because you rotated it by cis theta, and then cis theta again. But it's also the same thing as just rotating it by 2 theta. So it turns out you rotate it n times by cis theta. It's the same as rotating it 1 time by cis of n theta. And that kind of gives us this, which is nothing. It's a little bit looks daunting, but it's all it's saying is this. That's all it's saying. That's as simple as that. So we'll cover this. We'll recap that again in detail. But for now, back to roots of unity. This is just going to be equal to cis of 3 theta. So now it is what the only value of cis such that cis of something is 1 is 0. So when is 3 theta 0? Well, when theta is 0, it's of course going to be 0. When theta is 2 pi over 3, then it becomes cis of 2 pi, which is the same as cis of 0. So theta can be 0, 2 pi over 3, or 4 pi over 3. Because in all cases, we have this. Okay, so then our solutions are now just 2 cis 2 pi over 3 and 2 cis 4 pi over 3. And I'm not going to evaluate them, but you can evaluate them pretty easily by just using our definition, cosine plus I sine. Just for the sake of time, I'm not going to evaluate. And this is true in general, not just for 3, of course. And some other interesting properties about it. Now let's say we're looking at the solutions of, let's say, w to the 6th equals 64, let's say. The thing is, all of these are still going to be solutions. But there's going to be some additional solutions. So in general, the third roots of unity, they start at 0, and you go up by pi over 3 along the circle each time. The 6 roots of unity, you start at 0 degrees, you go up by pi over 6. But in doing so, you're also going to cover all the third roots of unity. Because, like the third roots of unity, are still 6 roots of unity. So if a question says, find all the solutions to this that are not solutions to this, then all you could do is you could write out all the solutions for this, and ignore the ones that ignore these solutions. So that's like kind of a cool thing. There's some, if you're new to this whole concept, there's some easier practice problems in the practice problem section below, which you can learn to, build your foundations if you're new to this topic. But if you're not, then this is most likely all just review for you, and you're ready to tackle some tricky problems like this one. Okay, how many integers n are there such that whenever these are complex numbers, we have this? Okay, we have to have the sum of all of them be 0. So the question is, we obviously need at least 2 complex numbers. One complex number is never going to have, that has magnitude 1, and yeah, that's the other thing. Because it has magnitude of 1, it's going to lie on the unit circle. Okay, so the sum of all of these is 0, first of all. So, is it possible with 2 complex numbers? Can they both have magnitude 1 and sum 0? Yes, of course. One example is we can just have it like this. This is an example of those problems where it's easier to think about it geometrically rather than trying to do this algebraically and deal with a bunch of stuff. Clearly, we can see these 2 points, they both have magnitude 1 and sum to 0. So n equals 2 works. What about n? Oh, such that the numbers. Sorry, I misremember the question. The question is saying whenever there are complex numbers such that this is true, then the numbers must be equally spaced. So the question is, if you have 2 complex numbers and they both sum to 0, what must happen? Well, this is like a complex number. You can think about it in the plane. You must have the diametrically opposite complex number in order for their sum to be 0. Because if you imagine this is like 3 plus, let's say this is like, I don't know, 1 plus 5i, for example. This has to be minus 1 minus 5i, which is exactly the point reflected about the origin of this point. So whenever there are 2, they must be equally spaced on the circle. If you have something like this, they're not going to add up to 0 because they're not diametrically opposite. So, and if they're diametrically opposite, they're clearly spaced evenly. N equals 2 is yes, this must be true. Now what about n equal to 3? Is it possible to have them not equally spaced, but they still overall, they sum to 1? And here's kind of like the key thing here. Without loss of generality, let's just say one of the points is here. Why? Let's say we have some other configuration that has sum to 0. We can just rotate it by cis of theta, all the points, and we end up with 1 point being here and the other 2 points being somewhere else. So without loss of generality, we can just say that, okay, let one of the points be here, and if it's not here, just rotate our entire diagram by theta degrees, and the sum of the complex numbers is still going to be 0, and all the magnitudes are still going to be 1. So now, the thing is, let's say our other complex number was here. Now individually, let's look at this. Let's call this is let's gonna have be 1, or let's call this I. So now what must be true about each of these complex numbers? They each must have, first of all, their x values must be equal. Their real parts must be equal and opposite of each other, because this complex number has no real part. So if this is, let's say, has a real part of a, this must have a real part of negative a. And the other thing is, if their real parts are equal, then they're symmetric about this line. And if they're symmetric about this line, it's kind of like the same point, except their real parts are flipped. So they're going to have the same imaginary part. So each of them must have an imaginary part of I over 2. Why I over 2? Because then their sum, or sorry, my bad, negative I over 2. So that now when you add them all to I, the real parts cancel, and the imaginary parts cancel with this I. Okay, but then the magnitude of the complex number is 1. So then what do we have here? Are these points equally spaced is the question. Are they always equally spaced? Well, we could see, notice that this complex number has magnitude 1. And that means the real part, in this case, must be minus square root of root 3 over 2, because that's the only real value such that this point will be 1 away from the origin. Anything else, the magnitude is going to be either more or less than this. If you here, it's going to be bigger than 1. Here, it's going to be less than. This must be the real part. And you can just do this by doing Pythagorean theorem. 1 minus 1/2 squared, which is root 3 over 2. Similarly, over here, we get the exact same thing. We have a squared plus 1/2 squared equals 1. So a squared is 3/4. A is either root 3 over 2 or minus root 3 over 2. So it's going to have to be root 3 over 2 because in our diagram, we see it's as a positive real part. Okay, so now the question is, are these equally spaced? And to do this, we use 30, 60, 90 triangles. This is root 3 over 2. This is half. So this is 60 degrees, 30 degrees. Similarly, this is 60 and this is 30. And then now by sum of angles in a line, we get that's 120 and that's 120. So clearly these points are equally spaced. So n equals 3 is also a check. Okay, now what about n equals 4? So now let's just erase all of this from our diagrams and we can start fresh. So now we have 4 points on the circle. Now the question is it possible that the points don't form a square, basically, in the complex plane? Is it possible that the points don't form a square? So let's just try it. Like earlier, let's fix one point to be here. And let's say maybe we put a point here. So now it's not going to form a square. We just put one point arbitrary, or rather, you know what? Here's actually a really cool construction I just found. What if we put one point here, and then we put our second point at the exact same point? Now these numbers are both I, complex numbers. Now similarly, we can put one here and put another one at the exact same point. They're both negative I. These are both I. They have a sum of 0, but are they equally spaced? No. This distance and 0 are not the same. That's just kind of a construction that works. You might be like, how did you think of that? The realization for me was, okay, we want to try and look at some other configuration. Will they be equally spaced? So I try to do the opposite. And I construct something such that when it's not equally spaced, it has a sum of 0. And then I thought, okay, from our 2 case, we had I negative I. That sum to 0. Now what if we just scale that by 2? Now we put 2 points here and 2 points here. That does work. So unfortunately for us, or fortunately, whatever you want, n equals 4 doesn't work. What about 5? And by the same logic, we can get that all even numbers are not going to work. Okay, but now what about n equal to 5? Does that work? Let's try and do something. What if we have an equilateral triangle like we had earlier? Remember, we had 3 points. So what we're trying to do is we found something that had 3, 0, with 3 points that sum to 0. And now what if we put these 2 points that also sum to 0. Or rather, we can do that anywhere. We can put another point here and a point here. Take a look at that. 5 points, they sum to 0. They're clearly not equally spaced. And again, the motivation here is we want to try and construct something for n equals 5 that's not equally spaced. So we look at our previous thing, we saw the equilateral triangle. And then we're like, what if we also add the n equals 2 case onto this? And we can put it in any way we want such that it's not equally spaced. So this condition is not necessarily true. Now for 7. It's the exact same reason it's not going to work. We can put a 3, and then we can just add 2, and then we can just add another 2 at the same exact point. Another pair of complex numbers. And for 9, we just keep adding points here and here. And that's an example of a construction where they're not equally spaced, but this condition is satisfied, both of them. So clearly, only 2 and 3 work. Our answer is just 2. This is a really cool problem if you ask me. It's a smart problem, uses complex numbers and a bit of cleverness to figure out the solution. The main cleverness was, of course, in this part. In my opinion, the 2 and 3 were pretty easy. Most people would be able to figure that out. But realizing how these don't work, because you can just kind of combine the previous cases, is kind of the tricky idea. Really cool idea in this problem. Okay, now back to this. Like I mentioned earlier, we have a point. We can multiply it by e to the I theta, or cis of theta, to get to a new point, theta degrees counterclockwise. And we also have this, DeMoivre's theorem, and this is just an alternative form of this. So what this is saying is, let's say we have a complex number z, which is of this form. We just express it like this. Now we take the r to the n out, and then the e to the I to the n. That just becomes e to the I n theta, which is just this. So that's kind of using DeMoivre's theorem. And this is really good for evaluating expressions like this, because we can just make this 2 times root 3 over 2 plus I over 2. So this becomes this. And now this, if you notice, it's just cis of 60. Now we just have 2 to the 8th, cis of 60 degrees to the 8th, which is nothing but cis 2 to the 8th times cis of 480 degrees. And this is pretty easy to evaluate using unit circle stuff. So you see how that's so much easier than doing that over and over again, multiplying. Yeah, when you have exponents, large exponents especially, the same thing can be true. We could make this root 3 plus I to the power of 2018, and the problem wouldn't be that much harder. Of course, we would have a 2 to the 2018 term, but evaluating this term doesn't really get harder as it gets bigger. Imagine doing that manually. Root 3 plus I times root 3 plus I, and then root 3 plus I again. That seems very, very tedious. Okay, now on to a problem that uses DeMoivre's theorem. Complex numbers z and w satisfy z to the 13 equals w, and w to the 11 equals z. The imaginary part of z is blank. Basically, find the imaginary part of z. Okay, so first thing you might just be like, you want to do it badly, substitute this in. And that's my first impulse as well. So we have w to the 11 to the 13 is w, i.e. w to the 143 is w to the 142 is 1. So our solutions are just the 142th roots of unity. There's 142 solutions for this. We're asked to find the imaginary part of z. W to the 11. Basically, it suffices to find what the value of w to the 11 really is. So here's kind of the idea here. All the solutions are going to be of the form this to w. They're going to be of the form this of 2 pi by 142. This of 2 pi by 142. This of 4 pi by 142. And this will go all the way until cis of 284 pi by 142, which is basically cis of 0, if you think about it. Just cis of 2 pi. So these are basically all of our solutions. And we're asked to find w to the 11. Basically, we just have to find w to the 11. So it's going to be of the form cis of, going to be like cis of 22 pi over 142. Or it could also be cis of 44 pi by 142. And so on. And we can actually simplify this. Why not? So all the solutions are of the form this. And take a look at what the question's asking. This is going to have an imaginary part of just sine 11 pi by 71. But it's only asking for this. So our answer is just 71. So a pretty simple problem. Key idea, write your equations, substitute, and get your hands down to roots of unity. On to the next one. This one's slightly more tricky. This one's going to use DeMoivre's theorem, I think. So z equals this, which is just cis 45. Because 1/2 is cosine 45, and 1 over root 2 is cosine 45 as well as sine 45. And I don't know why I wrote it with the color possible. And we're asked to find this giant looking expression. Z to the 1 plus z to the 4 all the way till z to the 144. All this times z to the negative 1 plus z to the negative 144. The key thing to notice here is z to the 8th is 1, because this 45 to the power of 8 is cis 360, or 1. Z to the 8th is 1. So really, it suffices to find these values mod 8, because that's all we care about. So these are just perfect squares. Is there a pattern mod 8? 1 squared is 1 mod 8. 2 squared is 4 mod 8. 3 squared is 1 mod 8. 4 squared is 0 mod 8. 5 squared is the same as 3 squared, 1 mod 8. 6 squared, 4 mod 8. Yeah, 4 mod 8. 7 squared is 1 mod 8. 8 squared is 0 mod 8. We've got this pattern kind of repeating here. 1, 4, 1, 0. 1, 4, 1, 0. Mod 8. So essentially, that's just going to get down to cis of 45 plus cis of 45 times 4, 180, plus, again, cis of 45, plus cis of 0, which is just 1. And this is going to repeat. There's 12 terms, so it's going to repeat 3 times. So this is just 3 times this, the first part. The second thing is nearly the same exact thing. In fact, I literally think it's the exact same. So let's take a look. Z to the negative 1, that's just going to be, let's see, z to the negative 1, or z to the negative 1, which is just squared all the way till z to the negative 12 squared. So negative 1 squared is just this of negative 45. Over here, we have something slightly different. This of negative 40, it's going to be the same thing, except all of these values are now negative. This of negative 180 plus this of negative 45 plus this of negative 0, just 0. Do you understand why this is true? Because it's the same thing as z, except now instead of z, we have 1 over z. 1 over z to the power of 1 squared. 1 over z to the power of 2 squared. And 1 over z is just cis of negative 45. We just have this. Now this is pretty simple to evaluate. This 45 is just root 1 literally given 1 plus root 2 over this. This of 180 is cosine 180, -1, plus I sine 0, or I sine 180, which is 0. And then again, 1 plus I over root 2, and then just 1. These terms nicely cancel. And this is something very, very similar. Except because we're dealing with negatives, now it's going to be just a little bit different. So 1 minus I over root 2. Here we just have system -180, which is the same as system 180, -1. Here we have 1 again, and here we have 1 minus I over root 2. So overall, we have 3, 1 plus I, root 2, times 3, 1 minus I, root 2. And this is just 9. 1 plus I times 1 minus I is just 1 squared plus 1 squared, so 2 times 2. Our answer is just 36. We're done. Pretty cool problem, where the key idea is DeMoivre's theorem. How we have sys of 45n is just this to the 45. So we simplified all of this by realizing that all we care about is this exponent mod 8, because sys cycles every 8. So yeah, how to solve, okay. And in the next video, we're going to take a look at how to use complex numbers to solve geometry problems. So for those of you who don't like geometry, you're not going to want to miss this next video, because we're going to learn another form of bashing. Just like coordinate bashing, now complex bashing. Check it out in the next video. You can find it over there.